Okay, so picture this. You get back from vacation. Your camera is just overflowing with photos.
Oh, yeah.
Hundreds, thousands maybe.
Yeah.
You know you're never going to sort through them all.
Yeah, who does?
But there you are, scrolling, scrolling, scrolling. Because you want to see every single photo of your adorable dog.
Of course.
But there's no magic dog filter.
Right.
So it's a scrollathon.
Yeah, that's exactly the problem computers faced for years, actually. Trying to make sense of images, just computationally.u, painful.
A real digital headache. But here's where things get interesting. Enter. Convolutional Neural Networks.
CNNs.
CNNs. In this deep dive, we're your tour guides, taking you from, ANN novice.
Mm-hmm.
That's artificial neural networks, by the way. Taking you from ANN novice to CNN pro. By the end of this, you'll be decoding AI image recognition headlines like it's nothing.
Absolutely.
And we've got some great material to work with, a research paper that breaks down CNNs and another on kind of the foundations of ANNs. Perfect combo,
Just
right?
absolutely. And you know what I like about these papers? They don't waste any time on the very basics, which means we can get to the really interesting, kind of mind-blowing stuff much faster.
Love it when that happens. Okay, so let's set the scene a little bit. Why were traditional ANNs so bad at handling images in the first place? What was it about a simple picture that tripped them up?
Basically, it boils down to this. Traditional ANNs just weren't built to handle how complex images are. Think about it. Even a small, blurry picture, 28 by 28 pixels.
Right.
That's still a ton of information for a computer to process.
Each pixel, like a tiny piece of the puzzle.
Exactly. Now scale that up to your average picture, 64 by 64 pixels. Suddenly, the number of connections, the relationships between all those pixels explodes. And each connection is another piece of information the ANN has to analyze.
Yeah, and the CNN paper uses this great analogy. Imagine each one of those connections is like a tiny weight you need to adjust.
I love that analogy. It's perfect.
And suddenly you're dealing with millions of weights just to process a single picture.
Exactly. It's like trying to solve this massive jigsaw puzzle, but the pieces keep changing shape on you.
Oh, man.
Yeah, the computational power needed was astronomical. The whole system was just incredibly inefficient.
So I'm starting to see why those traditional ANNs struggled. It's like, trying to understand a symphony. But you're only allowed to listen to one instrument at a time.
And only one note.
One note at a time.
Yeah.
You're never going to get the full picture, let alone appreciate the music.
Brilliant analogy. And that's where CNNs come in. They're specifically designed to handle that complexity, the complexity of image data, without getting bogged down, without drowning in a sea of pixels.
Okay, so how do they do it? What's their secret sauce?
It all comes down to their structure. Unlike traditional ANNs, CNNs are built in layers, and each layer plays a specific role in breaking that image down into manageable chunks of information.
Okay, so let's unpack this idea of layers a bit. The paper mentions three main types: convolutional, pooling, and fully connected. It's like a recipe for some kind of crazy cake.
And just like a good cake, each ingredient, in our case, each layer, serves a very specific purpose.
Okay, so let's start with the first layer, convolutional layers. What's going on there?
So think of it this way. Instead of trying to look at the whole picture at once, a convolutional layer uses a smaller window that scans the image bit by bit. Imagine you're searching for your dog in a photo.
Okay, yeah. I'm picturing my camera roll right now.
Now imagine you've got this dog-shaped magnifying glass.
Okay.
That magnifying glass, that's your convolutional layer's window or filter, and it slides across the image looking for anything that matches that shape. The stronger the reaction from that filter, the more confident the network is that it's found your dog.
So it's not just looking at pixels randomly, it's looking for patterns, like shapes and edges, the things that actually make a dog visually, right?
Exactly. And as that dog filter scans the image, it creates this heat map. The brighter the spot on the map, the more confident the network is that it's found a dog.
That makes so much sense. Okay, so we've got these convolutional layers. They're acting like expert detectives, scanning for clues. Then what?
Well, imagine your detective has pages and pages of notes now, right? Got to simplify things somehow. That's where pooling layers come in.
Time to drain the metaphorical pool of data.
Exactly. Pooling is all about simplifying that information, but keeping the most important stuff. So it's like, imagine shrinking that heat map down, keeping only the areas where the dog signal is strongest.
So it's like summarizing the detective's report.
Yeah.
cut out the extra details, highlight the key evidence.
You got it. And here's where it gets really clever. By focusing only on that most important information, CNNs can drastically reduce the computational power that's needed. They're much faster than traditional ANNs.
Ah, so it's not just about understanding the images, it's about understanding them efficiently. That's huge.
Absolutely. Now we've got our simplified map. It's highlighting those most likely dog zones. But how do we go from that to the CNN actually saying, yep, that's definitely a dog?
Right. We need a verdict. That's where the fully connected layers step in.
Exactly. This is the grand finale where all the pieces of the puzzle come together. The network takes those simplified feature maps from the pooling layers, uses them as clues to make its final decision.
Okay, so after all that detective work, the fully connected layer is like the judge in a courtroom, right?
Mm-hmm.
Reviewing all the evidence, making the final call.
Perfect analogy. It looks at all the evidence, the edges, the shapes, the textures, and based on everything it's learned from being trained on tons and tons of other images, it decides, dog or not a dog.
It's amazing how these CNNs really do mimic how our own brains work, breaking down this complex task into smaller, manageable steps.
For sure. And just like our brains, CNNs can be wired in different ways, and that's what we call CNN architecture.
Okay, so let's talk architecture for a minute. The CNN paper mentions that there's no single best way to build a CNN. Kind of like there's no one-size-fits-all brain, right?
Exactly. The best CNN architecture depends completely on what you're trying to get it to do. Think of it like building with Legos. You can use the same basic blocks to create a spaceship, a castle, even a dog.
So it's all about choosing the right combination of layers, the right sequence for the job.
Exactly. And just like a Lego master has their favorite building techniques, CNN designers have developed some really effective architectures for certain tasks.
Makes sense. Now, you mentioned earlier that you can actually peek inside CNNs, see how they're making decisions. That sounds super cool. Is that what figure 3 in the CNN paper is showing? The one with those visualizations of the handwritten digits?
That's the one. That figure is a great example of how we can visualize what the CNN is seeing. At first glance, it looks like a jumble of pixels, but if you look closer...
Wait, yeah, I see it. It's like the network is highlighting certain features of each digit, like the curve of a 2 or the straight line of a 7. It's learning to see the world in a way that makes sense for the task, for recognizing those digits.
Exactly. It's learning to pull out the most meaningful information from that raw data. It's kind of like looking at an X-ray, You're not seeing the whole picture. You're seeing what's most important for making a diagnosis.
This is blowing my mind. To think all of this is happening because of algorithms, lines of code. It's like cracking the code of vision itself.
It's pretty incredible. And this goes way beyond recognizing digits in pictures or dogs in your photo album. CNNs are being used in everything from self-driving cars to medical imaging these days.
So from finding our vacation photos to potentially diagnosing diseases, CNNs are changing the world.
Absolutely. But there's one more thing I want to touch on before we move on. Something that is key to making CNNs actually work in the real world, and that's training.
Ah, right.
Right.
Because the CNN is only as good as the data it's trained on.
Exactly. And this is where things get really interesting.
Okay, so we've talked about the building blocks of CNNs, those layers, and how they learn from data. But how does that learning actually happen? How do you train a CNN to, become a dog-detecting superhero?
It's all about training, specifically supervised learning.
Supervised learning. Sounds like you need a teacher.
Exactly. Just like we learn, by being shown examples, somebody giving us feedback. Well, CNNs are trained using these massive data sets, and they're labeled.
Labeled?
Yeah. Each image is labeled with the right classification, like dog, cat, bicycle, whatever it is.
So it's like this huge photo album, but every picture is carefully labeled.
Exactly. The CNN looks at the image, makes a guess, compares its guess to that label, and then adjusts little by little to become more accurate.
So it's trial and error, but it's an algorithm doing it, not a human.
Exactly. And it's through that training process that it gets so good at recognizing those specific things.
So it's not just seeing, but actually understanding.
Right.
Learning the rules of the game.
Perfect way to put it. And what's really mind-blowing is we can actually look inside the network and see those parameters changing. We can practically see it thinking, see its reasoning process.
It's like the CNN is saying, this is what I've learned about dogs. This is how I know.
Right. And that ability to learn from data, that's why CNNs are so adaptable. They can learn to recognize all kinds of things, even do things like identify medical problems in X-rays or generate totally new images that look real.
Wow. Endless possibilities. Now, the ANN paper mentions this thing, unsupervised learning.
Yeah.
And that sounds like Next level stuff. What is that?
Unsupervised learning is like the wild west of AI. It could change everything about how powerful CNNs become. Imagine a CNN that learns to recognize brand new things without any labels at all, just by observing.
So it's like a self-taught AI,
Yeah,
learning from experience like we do.
exactly. And we're just starting to figure out how to do it, how to make it work. The possibilities are, well, they're pretty much endless.
This deep dive has been amazing. My brain feels like it's been through a car wash. In a good way.
It's a wild ride for sure.
And the best part is, we've only scratched the surface.
Oh yeah, there's so much more to
For
explore.
everyone listening who wants to dive even deeper, the links to both of the papers we talked about, those are going to be in the show notes. Go explore.
Don't just take our word for it.
Exactly. The world of AI is changing every day, and we're all on this journey together.
Absolutely.
Who knows? Maybe someone listening to this will be inspired to build their own CNN someday.
That would be amazing. But for now, thanks for joining us for this deep dive into the world of convolutional neural networks. It's been a pleasure.
It's been a blast. And to all our listeners, thanks for tuning in.